Hey guys, this is Heather speaking. I'm going to take a few minutes to talk about what I did for my final project in hydrology. Now I only have 5 minutes to explain something that took me many hours to complete, so just bear with me. So the end goal of this project was to design a detention basin to equalize the maximum expected flow for a selected watershed. To do this, I had to first pick a watershed to analyze, determine the maximum expected flow of the watershed, and then design a detention basin to control that flow. Since I go to school at the University of Utah, I wanted to select a watershed nearby. So here's the one I chose, and here are the coordinates of the point of analysis, or the point in which all the water will drain to. This is where the detention basin will be designed. I used many tools to help me on my project, with the first one being StreamStats. All I had to do was punch in the coordinates and out came a nicely delineated watershed that I could use for my analysis. StreamStats also provided me the area, percent of developed land, and the downloadable shapefile. It also showed me where the channel flow occurred within the watershed. The next tool I used was the Web Soil Survey. All I had to do here was import the StreamStat shapefile, and it would spit out all of the different soil types that were contained within the watershed. There were a total of 7 soil types, and these divided areas became the subbasins of my watershed. I then used Google Earth Pro, which has easily become one of my favorite tools to use in civil design. I imported the StreamStat shapefile, and then I used the line tool to draw the approximate path of channel flow, and the polygon tool to draw the approximate shape of each subbasin. I was then able to approximate the different flow types in the subbasins, such as sheet flow, shallow concentrated flow, and channel flow. I especially like Google Earth Pro because it makes it easy to determine lengths and areas. It also provides a good aerial image so that the type of ground cover in each subbasin can easily be determined. Another awesome thing that Google Earth Pro does is elevation profiles. This helped me find the average slope of each flow path. I was then able to apply this information to some of the watershed analysis methods described in the TR55. I used a bunch of tables and figures so that I could use these handy equations to estimate the runoff and calculate the time of concentration. After that, I was able to snag some site-specific precipitation data from the NOAA Atlas Point Precipitation website. The data that I was most interested in was the 1-year 24-hour design storm and the 100-year 24-hour design storm. At this point, I was finally able to plug in all of my calculations into HEC-HMS, which is a hydrologic modeling system designed to stimulate the complete hydrologic processes of watershed systems. HEC-HMS generates data for both the runoff and infiltration of each subbasin. Here is the data that it generated for my watershed. It also provides a global summary that gives a lot of good info about each subbasin, junction, and reach within the model. The last junction of the model is particularly important because it provides a peak discharge for the entire watershed. For the purpose of this project, I developed a model of the 100-year storm for both the watershed as it exists currently and another that assumes that the watershed is completely developed. The fully developed watershed is going to represent the absolute maximum flow expected to occur within the watershed in the future, while the model representing the existing development will represent the minimum allowable flow to be released from the detention basin. So I spent some time adjusting the size of the detention basin and the outlet structure orifices to produce the results I wanted. A peak inflow into the basin equal to the fully developed watershed peak discharge and a peak outflow of the basin equal to or within 5% less than the existing watershed's peak discharge. This figure shows the detention basin outflow as compared to the pre-developed 100-year storm runoff. Once I got a realistically sized outlet structure and detention basin, I needed to determine a pond inlet and outlet pipe sizes so that the flow could be controlled. There are 2 ways you can do this. The first is that you can either use these graphs or you can use an equation. Since the graphs look super confusing and I find it exceptionally easy to plug and chug values into an equation, that's what I did. The final inlet pipe sizes turned out to be 8 feet in diameter while the final outlet pipe size was 4.5 feet in diameter. This seems huge, but it's because there's a lot of flow. Or it might be because I did something wrong. Both are equally possible. Regardless, I went on to develop the design of an outlet structure based on my work. The final design was a 5 foot by 5 foot by 5 foot box with 2 orifices to allow for water to drain. So here's the drawing of what the final detention basin design would look like. Of course, it is not scale, but it provides a good representation.